by introducing a decaying learning rate and multiple update per steps. It achieved faster convergence, higher cumulative reward, and lower variance. This make learning more reliable under volatile conditions such as bursty task arrival and fluctuating wireless channel. In short, the progression is very clear here. Deep Edge SARSA stabilizes learning. Tara scale it to multiple agent system, and Tara optimize accelerate convergence and improve consistency. Now we'll move it to the experimental setup. We design a simulation environment that closely mirror real mobile edge computing dynamics. IoT device generate tasks following a Gaussian process. Wireless channels are modeled using relay feeding, and edge server operates under finite queue constraint. Reinforcement learning agents are trained under Sarsa Lambda, Q learning, and actor critic paradigm depending on the framework. This setup ensure that our experiments reflect realistic edge scenario. We run experiments with varying episode, typically between 20 and 300 episode to analyze convergence behavior. The statistical validations we repeated trial 30 times, often with 50 episode per trial, ensure robustness of results. In multi-device experiment, we use 5 devices and 2 server, which provide a realistic yet tractable scenario for testing scalability. The Q network architecture consisted of dense layer with ReLU activations and batch normalizations, which ensured stable training. In hybrid dual head variant, the network split into 2 head, one for Q value action estimations and one for state value estimation. This separation stabilizes and reduce variance compared to single head design. The reward function is central to the simulations as it penalizes both energy consumption and decay, weighted by lambda and beta respectively. Energy include both transmission energy and local computation energy, while delay include edge and local execution delay. By tuning alpha and beta, we can emphasize either energy efficiency or latency minimization. In practice, balanced weight were chosen to achieve Pareto optimal trade-off. This reward design ensure that the agent learn policies that are not only efficient, but also fair across devices, directly supporting the objective. Hyperparameters were tuned carefully to balance convergence and speed and stability. Learning rate were tested between 0.005 and 0.001. Discount factor gamma ranged from 0.95 to 0.98, reflecting importance of long-term rewards. Eligibility trace decay lambda was varied between 0.7 and 0.99, and lambda, which is equivalent to 0.9, yielding the most stable learning outcome. Excuse me. Exploration followed as epsilon greedy policy starting with at epsilon 1.0 and decaying gradually to 0.01 with decaying rate between 0.995 and 0.998. Episode range from 20 to 300 depending on the experiment, allowing us to study both short-term responsiveness and long-term convergence. Tara is evaluated on a multi-device edge computing environment where task arrives stochastically. The state captures queue length, channel gain, server load, and transmission rate, normalized to 0 and 1. That action include local execution, edge offloading or cloud offloading. Episode consists of 500 steps with task arriving according to Poisson distribution. which is simulating realistic traffic. Now we treated three Tara variant alongside five baseline, including acid critic and heuristic method. The baseline Tara uses a shallow dwelling network, while optimized variant employ deeper network and adaptive trees. All agents were implemented in TensorFlow 2.x and trained for 100 episodes with CPU parallelization. This setup ensures fair comparison across reinforcement learning and heuristic approach. Hyperparameter were tuned to balance the stability and responsiveness. Learning rate was set to 0.001 with decay applied in optimized variants. Batch size range from 64 to 128 and update bus still varied between 1 and 3. Replay capacity was fixed to 5,000 transitions with prioritized replay enabled in phase 2. Uh, Trace decay lambda was either fixed at 0.99 or adaptive dynamically between on the variant. Uh, Reward function in Tara penalizes both delay and energy consumptions while incentivizing the task through output. Weights and empirical tuned where alpha is 0.1 and 0.1 for a delay, and beta is 1.0 for energy, and gamma 0.1 for task process. This cooperative reward ensures fairness across device and balances efficiency and responsiveness. By aggregating reward, Tara stabilized performance in a multi-device environment. I model the mobile as computing a floating problem as a markup decisions process. The state space includes the buffer occupancy, channel gain, CPU frequency, and queue state. The agent chooses between local execution or uploading. This reward function penalizes both delay and energy consumption, encouraging efficient task management. The objective is to maximize cumulative reward over the time. To evaluate performance of all the agents, we train under identical traffic and channel conditions. Metrics include reward convergence, delay, energy efficiency, and stability. I compared my model against strong baselines such as Rainbow, DQN, delay heuristic to validate improvement. Result and discussion. For training, I integrated eligibility trees to propagate delay reward, ensuring correct credit assignment. The well-head neural network separate value and advantage stream, which stabilizes learning. Replay buffer were used to improve simple efficiency. Hyperparameters such as best size, learning rate, and discount factors were tuned for fair comparison across agents. This slide shows learning dynamics of deep edge SARSA. The model convergence steadily with stable rewards, acquisition beyond episode 600. Unlike PPO and DQN, no abrupt collapse were observed, indicating robust learning through eligibility trace. Comparison or this table compared the performance of different reinforcement learning algorithm for mobile edge computing task uploading. Tabular SASA lambda shows highest delay and reward variance, indicating a weaker stability. DQN and PPO improve delay and energy efficiency, but still shows higher variance compared to our framework, Deep Edge SARSA, which achieved the lowest average delay, 102.8 millisecond. Comparatively competitive energy consumption 0.87 joules, and the most stable reward distribution standard deviation 0.041. This confirmed that deep edge SARSA balanced fairness, convergence, and efficiency better than the baseline algorithm. This is a graph which shows its competitiveness. Hyperparameter sensitivity. Hyperparameter sensitivity analysis shows that higher learning rate improve convergence and reward accumulations. The optimal balance was observed near 10 to the power minus 3, confirming the robustness of deep edge SARSA under different training setting. We evaluated system level performance separately for each framework. Deep SARSA shows significant improvement in average task delay and energy consumption compared to conventional DRL baseline. Tara extends this, supporting partial uploading and multi-server collaboration, which improve throughput and fairness across the agent. And Tara optimize further enhance the system level outcome, accelerating convergence, leading to higher accumulations and report more consistent task success rate. Statistical validation, which confirm that deep edge SARSA's improvement are consistent and significant. Both paired t-test and Wilscon signed rank test shows strong evidence that the model outperformed PPO and other baseline. Learning level metrics. Here, each framework is again evaluated independently. Deep edge SARSA demonstrates stable reward dynamics and reduced variance. And delay feedback. Tara highlights stability and responsiveness in multi-agent environment, balancing delay and energy trade-off, and Tara optimized refined training behavior. This is the deep edge SARSA system level performance. So deep edge SARSA reduce average delay by 27% versus tabular SARSA lambda and 18% versus DQN. Energy consumption remain competitive within 5% most efficient baseline, and reward variance is 40% lower than PPO, confirming stability. Deep SARSA learning level performance, where Dwell had designed decoupled Q value and V value estimations improve stability. Eligibility trees propagate delay reward, better temporal credit assignment, and hypersensitivity confirm robustness across lambda, epsilon, alpha, and alpha variation. Okay, let me. The Rainbow DQN achieved the lowest delay, but consumptions more energy. Tara balanced delay, and okay, I will just come back to the system level of Tara. This is the system level result for Tara, where we can see Rainbow DQN. Delay is 3.75, A3C is 4.00, Tara is 4.25, and energy heuristic 5.50, delay heuristic 3.50, and hybrid heuristic 4.0.
मैं अभी इसका बुलाया था तो शैलेंद्र का अच्छा वो बताया कि अभी
So learning level result for Tara, the agent Rainbow is equivalent 2.95 and EC3 is 2.75, Tara so equivalent to 2.50, and Tara optimize is equivalent to 0.2012. It's a scale. Now, if you look at the performance comparison of the framework, so just move my slide. Okay, I'm so sorry for the delay. This table consolidate performance metrics across all framework. Deep edge SARSA, which reduces average delay by 27% compared to tabular SARSA, while the maintaining competitive energy consumption and achieve the lowest reward variance. Tara extend this to multi-agent setting, balancing delay and energy, achieving higher throughput and ensure fairness. across the agent. Tara optimize refined training strategy, delivering faster convergence, lower variance, and highest throughput while maintaining the fairness. In short, Deep Sarsa stabilizes learning. Tara scale it to multi-agent system, and Tara optimize accelerate convergence and efficiency. So we presented result into two dimensions. The system level rainbow DQN achieved lower delay, but the cost of higher energy, while Tara balances delay and energy and ensure fairness across regions. Heuristic baseline shows extreme trade-off. At the learning level, rainbow DQN converge quickly, but is unstable. A3C shows is slower but moderately stable, and Tara improves stability through eligibility trace. Tara optimizes further refined training, achieve the faster convergence and lowest variance. Together, this result validate the progression from stability to scalability to optimization. This slide shows reward convergence. Rainbow DQN converge at minus 0.31, but with instability. Tara and Tara optimize stabilize around minus 0.11 and minus 0.12, showing smoother convergence. Delay heuristic achieves minus 0.19 but lack adaptability. This confirms that trace-aware learning improves stability under delay rewards. Here we see delay energy trade-off. Rainbow DQN stabilizes at high delay and energy. Delay heuristic minimizes energy but consumes more energy. Tara achieve balanced outcome. Tara optimize further improve delay while maintaining energy efficiency. This demonstrates the advantage of trace-aware reinforcement learning. The trace and lambda balancing metrics validates the uniqueness of Tara. Only Tara variant report non-zero values showing effective trace-aware learning. Rainbow DQN and heuristic do not track this sign, which explain the instability under delay reward. So we can see here the comparative performance of Tara variant and baseline. So Tara variant against baseline agent. First looking at the reward performance, Rainbow DQN records the lowest reward, while Tara variant maintain the moderate value. Although all agents converge to negative reward under the chosen penalty structure. So Tara demonstrate more consistent stability compared to Rainbow and A3C. In terms of delay energy trade-off, Tara optimize achieve the lowest average delay with a moderate energy consumption. The hybrid heuristic is most efficient, most energy efficient, but suffer from the higher delay compared to Tara. For lambda balancing, Tara variant consistently maintain the value around 0.90 to 0.93, showing stable control between delay and energy objective. Baseline do not explicitly optimize lambda, which limit their adaptability. So finally, looking at the eligibility trace, only Tara variant reported non-zero value, such as 11.569. The Tara reported non-zero value. If you look at the eligibility trace, it's non-zero value. Baseline like Rainbow and AC3 reported with a zero value. And of course, I have not put here some of the figure. I'm so sorry. Here, the baseline like E3C. Okay. Overall, this result confirmed that Tara variant achieved balanced delay energy trade-off while leveraging eligibility trace to improve the Tara optimize. Uh, we summarize the statistical validation of our results. First, we confirm learning agents significantly outperform heuristic baseline with p-value less than 0.01. Second, rainbow DQN significantly higher reward compared to Tara. And finally, comparing Tara with A3C, the difference is not statistically significant, with p greater than 0.05. Uh, this validates reinforcement that Tara achieves stability comparable to predict method while consistently outperforming heuristic. It shows that our architecture is competitive, reliable, and suited for volatile ABC environment. Limitations. My work has some limitations. The experiment were conducted in single device, single server, mobile age computing scenario with limited stability. Fairness among multiple device was uh, is explored in Tara, but in deep learning it was limited. Security aspect such as adversarial offloading were not considered, and finally the models were evaluated in simulation, and uh, it is not yet embedded into the platform. Future direction. The future work will focus on extending deep edge SARSA and Tara to decentralized multi-agent setting, enabling scalable coordination among devices, hierarchical task uploading, and adaptive trace modulations. Uh, could further improve the efficiency. Benchmark on real hardware such as HTPU and mobile GPU will be validate deployment readiness. Finally, integrating 5G and 6G network will open applications in autonomous vehicle, robotic, and latency critical IoT settings. Mapping of the work to fulfillment of objectives. Uh, Objective one, focus on identifying challenges of deploying deep learning model on IoT devices. So here we have already synthesized issues such as latency, energy, and consumption, and heterogeneity bottleneck. This gives us the foundation of the problem formulation. Objective two, for analyzing edge server architecture for computations uploading. Uh, Here we reviewed single tier, hierarchical, collaborative, and fog-based mobile edge computing setup. We compared local, partial, fully, and cooperative uploading strategy, highlighting trade-off in latency, energy, and scalability. And goal three was about designing optimized cloud edge analytics models. So we propose Deep Sarsa and for fairness and convergence, and Tara for scalability. This framework validate through Python simulations showing their practical feasibility. Together, we represented the progressions from identifying bottleneck to analyze architecture to design new framework. Um, Goal 4 focuses on evaluating the performance of our proposed models against existing baseline. We benchmark deep edge SARSA and Tara against PPO, DQN, and classical SARSA. The result demonstrate improvement in fairness and convergence, speed, and scalability, confirming the viability of our framework. Objective 5, to situate our contributions with the broader age intelligence research landscape. So Reinforcement learning alongside transformer-based architectures such as TinyBird, Mobile BIT, and EageFormer. This establishes a dual pathway for future research, adaptive RL for decisions making, and transformer for subtotemporal coordinations. So this complete the not only did we validate our models against the strong baseline, but we also aligned them with emerging trend in edge intelligence, ensuring relevance for next generation mobile edge computing system. My publications is already published, present the mathematical analysis for trace-aware reinforcement architecture, validating its feasibility for mobile edge computing. This is published on International Journal of Applied Mathematics. The second paper is scheduled for publication on 10th January 2026, as confirmed from the publisher in the Advanced Engineering and Science. Is a comprehensive survey of deep learning approach for task uploading in mobile edge computing. This survey situates my contributions within the broader research landscape. Together, this publication demonstrates both theoretical and innovation and broader contextual synthesis, strengthening the impact of my work. This is the copy of the published paper. This we have received for the acceptance of the paper, and this paper, as promised by the publisher, will be published on 10th of January 2026. Currently, I have 3 journal papers under review in SCI and Scopus Index. One is this deep edge SARSA, trace aware well-head reinforcement learning for temporal credit assignment. This is being submitted to Journal of Computer and System Science. We have another paper, efficient task uploading in mobile edge computing via deep reinforcement learning with trace aware adaptation. This is this paper is under review on Informatica, the International Journal of Computing and Informations. And the third paper, Imagine Trained in Transformer-Based Deep Learning for Task of Uploading in Mobile Edge Computing, a systematic review. This has been submitted to Journal of Cluster Computing, and it is under review. 2 conference papers were already presented. One is trace-aware reinforcement learning architecture, TARA, for task uploading in edge network. It is presented in ICCIT 2025, British University, Vietnam, presented on 12th December. Recently, 2025, time and energy trade-off for mobile edge computing, comparative survey for task uploading strategy. It is this paper was presented to ICAET 2025. It's a Cummins College for Engineering, Women, Pune. This is IEEE Scopus Index, and this paper has been published as a conference proceeding. This is a certificate for ICAET 2025. British University certificate has not yet been given to us. So maybe in a day or 2, they will provide a certificate. So in conclusion, my work has systematically achieved all 5 objectives, from identifying bottleneck and designing and validating the reinforcement learning framework for mobile edge computing task uploading. The proposed model, Deep Edge SARSA and TARA, were validated through extensive simulation and demonstrated significant improvement in fairness, convergence, stability, and energy, scalability, and energy trade-off. In terms of dissemination, I have 1 journal paper already published, another is scheduled for publications, and 2 conference papers presented in IEEE Scopus Index venues, meeting the university's requirement for the I hope this meet the university requirement for the thesis submission. In addition, 3 more journal papers are under review in SCI Scopus Index Journal. Therefore, I have completed the work, achieve the objectives, and fulfill the publications criteria based on the university guideline. The thesis draft is also ready and on a final stage for submission. So I seek your permissions to allow me to submit my thesis. Thank you everyone for your time and patience and for listening to these presentations. And these are my reference. Some of the reference I have put, all the reference I could not put it here because it's almost reaching to 200. So I have kept it only around 30 references. So thank you so much. And if any questions.
Yeah, thank you, Mainul. So this is the whole summary of the works that Mr. Mainul Hoque done during this 5-year tenure of his PhD journey. So as you can see that all the objectives are fulfilled. Accordingly, 2 journal papers published. One is published, another is going to be published, accepted, going to be published on 10th of January. Both are Scopus, QT journals, and 2 international conferences presented, and 3 more are in review. We are expecting positive response from that side because already we got few comments. So now I would like to request the respected members to put forward their comments and suggestions, and so that Mainul could go for the next stage, that is the submission of this thesis. Thank you. Am I audible? Hello?
Yes, sir, you are.
Yes, you are.
And I would also like to request all the members to turn on their video cameras, videos, means cameras, so that we can take a screenshot of all the members.
I think it is okay.
Yeah, thank you, sir. He is our Dean Researcher, Dr. Kundu sir. So we are really privileged to have Dr. Kundu sir with us. And with our external members throughout his journey, PhD journey, sir has really suggested many things and improve our work. He is Dr. Rubul Kumar Mania sir, and I would like to thank you, Dr. Rubul sir, for his suggestion and comments and improvement during this 5 years tenure of the Mainul Hoque's PhD journey. Thank you, Rubul sir. And with us also Dr. Nazrina Rahman. Earlier, she was a faculty member of our university, but then she went to IIT Guwahati for her postdoc journey. So she was also a member, and now we are very happy that Dr. Nazrina joined in this Pre-Thesis seminar, because this is going to be the last seminar. So thank you, Dr. Nazrina. Professor Ratan Kumar Saha sir, our PhD sir. He is also here from the very first progress. So I would like to thank Ratan Kumar Saha sir for his valuable comments throughout these different seminars and progress of Mainul Hoque's PhD. Thank you, Saha sir.
Yeah, thank you. Thank you, Dibya. Thank you, Research Dean. And one question is there. If you go to the first algorithm you have discussed, I think see slide number around 62 or something. So inverted there, you have used the symbol inverted. Here, yes.
Yes, sir.
Update eligibility. What type of update you are talking about here?
So here, sir, can I get your questions?
I want to know, I mean, update eligibility, what is actually updating? You are updating what?
So basically, what happened is this eligibility trees. What it does, it it keeps on taking the back informations. Like I'll just explain you what exactly this does. Okay, uh, I'm just getting a call,
Okay,
so sorry.
no
Okay,
problem.
so here what we do is I'll just explain it to you. We begin the initializations of Q network parameter with eligibility trees along with the learning rate and discount factor and trace decay. So at the start of each episode, the environment generate IoT task and the agent observe the initial system rate, system state, Q channel and
Okay,
condition and CPU frequency. So at each
okay,
time, the agent select an offloading action using epsilon greedy policy. So this which balance the exploitations and exploration. Uh, then choose the action is executed and the task may be processed whether locally or to upload to the edge or sent to the cloud. So here actually what happened, the agent received a reward which penalized both the delay and energy consumption, ensuring the energy trade-off. And then next, the agent observe the new system state and select the new system state and next action. So the temporal difference error is calculated, which measures the gap between the predict and the actual outcome. So the eligibility trace are updated, and this mechanism propagate credit backward across multiple steps, allowing the agent to learn effectively even when the reward is delayed. So
okay,
this,
okay. Okay, I understood. Okay, okay. So the inverted delta zero is
so
basically
yes,
backward,
sir. This it's a updated, yes, sir. Backward delay, sir. So
backward. Okay,
yes, sir.
okay,
It's basically updated using the temporal difference arrows.
okay, 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 okay. Good. Okay.
Thank you, sir.
Mhm.
Okay, thank you, sir. And like to request, actually, Rubul sir, his university exam is going on. He was there, but he need to go for some investigations. So that's why I think he's not able to speak. But he was there in the beginning. So now I would like to request Mainul sir to come to the university so that because I think I can expect that all the members agree with his work, that his works can be submitted now. Yes, sir? Dean
Yes,
Research, sir?
agree.
Yeah, thank you, sir.
Agree that he should submit.
So,
Yes, sir.
as we move to the end of this year, because we have only a few days left, so I'd like to request Morning Sir to come to the university. And the next process means printing out of the thesis and some forms you have to fill up. Our Dean
Yes, sir.
Research Sir will guide us during this process. But this will be possible only if we can start it means at earliest. So, Morning Sir, please come to the university if possible this
Yes, sir.
week only. Okay,
Okay, sir.
because we have
Okay, sir.
our break is going to be started from 25th.
Yes,
So
sir.
I can expect that within 7 days we can complete this task.
Yes, sir.
Okay. So then, thank you everybody. Thank you, Ratan Kumar Saha sir. Thank you, Dr. Rubul sir, Nazrina ma'am, and thank you, respected Dean Research sir. Now, with your permission, we are going to conclude this pre-thesis seminar. If you all
Okay.
agree.
Yes, yes, you can submit now.
Okay, thank you.
No, I think okay.
Yes, sir, thank you, sir. So, Mainul sir, so please come with the draft copy.
Yes, sir.
Once I'll check physically, and as the soft copy I'm already checking, but the virtual, this means draft copy I have to check, and then
Yes, sir.
we go for the submission process. Okay.
Sure,
Thank you,
sure,
everyone.
sure, sir. Thank you, everyone. Thank you, sir.
Thank you, sir.
Okay, thank you.
Thank you, sir.